Well, thank you again. And on behalf of the education and research centers throughout the country, we're pleased to present the Industrial Hygiene webinar series, offering free webinars the second Tuesday of each month. This collaborative effort is on behalf of each ERC's continuing education program and aspires to provide access to current research supported through NIOSH ERC programs. We appreciate you being here with us today. Today's webinar, Data, Professional Judgment, and Modeling, and Occupational Exposure Assessment, is brought to you by Johns Hopkins Education and Research Center for Occupational Safety and Health and Dr. Ramachandran. A few housekeeping items first. You're going to be muted during this presentation. If you'd like to ask a question, please enter it into the online Q&A. We'll save time at the end of the presentation to answer questions. All participants who logged in with the registration email for the live presentation today will receive a link to the recording and an evaluation form via email. This evaluation form will also qualify you for a certificate of completion with one continuing education contact hour. Once the evaluation is completed, you'll be able to access and print your certificate. This presentation is also being recorded and will be made available on the CREH Northern California's YouTube page and on our website, where you can find all the other ERC webinars that we've done this year. At this time, I'm pleased to welcome our presenter. Dr. Ramachandran is a professor in the Department of Environmental Health and Engineering in the Bloomberg School of Public Health at Johns Hopkins University, and also the director of the Johns Hopkins Education and Research Center for Occupational Safety and Health. He has conducted research in various areas relating to human exposure assessment in occupational, residential, and outdoor settings. He's also served as a member of the Board of Scientific Counselors to the National Institute of Occupational Safety and Health, or NIOSH, advisory committees for the National Academy of Sciences, and the U.S. Environmental Protection Agency. He's also serving on the editorial boards of the Annals of Work Exposures in Health and the Journal of Occupational and Environmental Hygiene. He has a bachelor's degree in electrical engineering from the Indian Institute of Technology, Bombay, a master's degree in environmental engineering, and a PhD in environmental sciences and engineering from the University of North Carolina. Thank you so much for joining us today, Dr. Ramachandran. We're looking forward to your presentation.
Thank you very much, Michelle. And thank you all for giving me this opportunity to talk to you. We are very on behalf of the Johns Hopkins ERC, I'm very happy to participate in this seminar series. So today what I wanted to do was talk about some aspects of my work that have been of sort of great and enduring interest to me throughout my career on the uses of data, professional judgment, and models in occupational exposure assessment. So it sort of is a partly walk through time in my career and also partly looking forward to the next phase of where this area of research is carrying all of us in this profession. We can start by thinking about, well, what do industrial hygienists do? And at a very fundamental level, our job in this profession is to ensure that all the workers under our care have access to safe workplaces, and no worker has an unacceptable level of exposure to any kind of hazard in the workplace. And we do that through various exposure assessment strategies, and there are a number of strategies out there, and we'll talk about some of them. And the goal is to attain this sort of metric, meaning minimize the number of workers who have unacceptable exposures using sort of a minimal amount of resources. So we are trying to optimize this sort of conflict between efficiency and meaning the how easily we can achieve this goal with minimal resources and make sure that most workers or almost all workers are protected, namely the effectiveness of our strategy. It's important to get this part right, the exposure assessment right, because many of the other things that industrial hygienists do are dependent on this. So whether it's compliance, or whether we decide to do hazard communication, whether we decide to put workers in medical surveillance or additional monitoring, the types of controls we want to put workers in, whether it's engineering, practice or administrative controls or personal protective equipment. All of these decisions are based on an assessment of exposures. And if we get that wrong, then the decisions regarding these other aspects of our job will also be flawed. And to just put this in context, I'll give you an example of a medium-sized manufacturing facility. And on the left-hand side, you see these various departments in this facility: production, maintenance, engineering, and so on. And you see the number of employees in each of these departments. And you can think about the types of exposure tasks that people in these departments do. Um, and this is a modern chemical manufacturing facility, so it's a reasonable assumption that each task involves roughly 15 chemicals per task. So the last column on the right gives the chemical task combinations. So each exposure task multiplied by 15 chemicals per task, so that's chemical task combinations. And you see that that's a fairly large number. And in fact, the number of these chemical task combinations, or what we refer to sometimes as similar exposure groups, is about 1,400. So 1,400 similar exposure groups in this particular facility. And if we can then further say, okay, we have roughly 250 working days in a typical year and 2 shifts per day, we will have roughly 700,000 exposure opportunities. And this is at the level of the exposure groups. We're not even talking about the workers in each of these exposure groups. And so that's a lot of exposure opportunities. And if you then say, okay, what is the typical or most common number of samples that we use to make a judgment about exposure, whether it's, are we in compliance or not, are we above some exposure threshold or not. And some of you probably have encountered this question in many of the PDCs that I have taught. And certainly many of my students know of this question, which I routinely ask, and some of my colleagues also routinely ask. The most common number of samples used to make a judgment about exposure is 0. And so we have a large number of exposure opportunities, but the number of measurements we make to evaluate these exposures is 0. And the next most common number of samples is 1, and then the next one is 2, and so on. So we, as a profession in industrial hygiene, are plagued with very small sample sizes. And there are very good practical reasons for this. The main one being that it is very expensive to make exposure monitoring measurements. And so we rely, in the absence of samples, we rely on other ways in which we can evaluate and assess exposures. And so more than 90% of the exposure assessments are conducted without personal monitoring or personal exposure measurements, and instead we rely on what we call as professional judgment. And this professional judgment in quotes, because we quite often do not know how good or bad these judgments are. And so that's part of what I'll be talking about today. So how good is this professional judgment, since we rely on this so heavily? And so in the next few slides, I'll be talking about some of the studies that I and my students over the years have conducted evaluating the accuracy of exposure assessments in 2 different contexts. One is in routine industrial hygiene operations. And so we look at the accuracy when we are relying only on professional judgment plus very sparse 1, 2, or 3 very small numbers of data, and then even less frequently when we use mathematical models. The second context, and I'll touch upon this also in my talk, is how good are exposure assessments done in the context of epidemiological studies. And both of these were motivated by my sort of experience in over last 25 years. Back when I started my career in industrial hygiene, I was sort of struck by the heavy reliance on professional judgment in this field. Um, and I wanted to know how good these professional judgments were, um, and that is sort of motivation of this over the last couple of decades. So as you all know, industrial hygienists have um, exposure assessment strategy that is loosely based on the strategy that I'm showing the diagram for. This is the American Industrial Hygiene Association strategy. Um, and the strategy starts off by the industrial hygienist gaining an understanding of basic processes and the chemicals and the nature of work that the workers are conducting, the availability of controls, and their efficiency of these controls, and so on. And on the basis of that, the workers are divided into similar exposure groups, and then an exposure is assessed for each of these exposure groups. And these exposures are then compared to some kind of an exposure limit. And on the basis of this comparison, the exposure is deemed acceptable, in which case you're good, unacceptable, in which case you need to think about imposing some kind of controls. And then finally, you end up with an uncertain result, in which case you need to go out and gather more information. And in terms of when I say evaluate exposure, we are really talking about looking at a particular decision statistic in the exposure distribution of workers in this particular similar exposure group. And as a sort of a matter of general consensus, this profession has arrived at some kind of upper percentile, and quite often it is the 95th percentile, but many institutions and companies use other percentiles such as the 90th percentile or maybe the 99th percentile. But for the purpose of this talk, we'll consider the 95th percentile as the decision statistic. And by that I mean we compare this 95th percentile against some fraction of the exposure limit. So if the 95th percentile is less than 10% of the exposure limit, we feel like, okay, that's a relatively low exposure, and we can get away with providing the workers with some general hazard communication information. If it's the 95th percentile is between 10 and 50% of the exposure limit, we provide more chemical specific hazard communication. And when we are between 50 and 100% of the exposure limit, that is, we are uncomfortably close to the exposure limit, then we say, okay, I need to really take a lot more monitoring measurements, maybe put people in medical surveillance, maybe observe and understand work practices better, and so on. And then finally, when we are out of compliance, the 95th percentile is greater than the exposure limit, then we need to look at work practice controls and putting people in different types of PPE and so on. So there is a sort of well-defined way in which decisions can be made. But we are never sure about the accuracy of our decisions. And so we need to be able to represent our uncertainty in our decision. And so the figure on the top right shows a way in which you can represent the uncertainty in your decision. And here, for example, we can say that my decision is that it is a category 1 exposure. The 95th percentile is less than 10% of the exposure limit, but I'm only about 70% confident in that decision. And there are sort of lower levels of confidence in these other categories. So given that sort of basic framework, we can sort of look at some examples. So we can say, okay, let's say we have a situation where we have 3 samples taken on an exposure group, and then what we would do is we'll say, okay, that's too small to evaluate on its own, but we are going to assume that these data come from an assumed underlying skewed log normal distribution. And using that assumption, we can calculate the 95th percentile of this log normal distribution, and it turns out to be 9.45. And let's assume, for the sake of this example, that our exposure limit is 10. And so we say, okay, there are three data points. The point estimate of the 95th percentile is nominally less than the exposure limit. However, there is a great deal of uncertainty around this 95th percentile, extending well beyond the exposure limit. So, this is where we are if we just look at small numbers of data. Another way to approach it is say, okay, I'm going to use a very simple model, and I'll just express the concentration, the exposure, as the ratio of the rate at which contaminant is being generated in this work area, and divided by the rate at which the contaminant is being removed by ventilation for this airborne contaminant. And I'll assume some uncertainty in each one of these parameters, and I'll do what is called a Monte Carlo uncertainty analysis, and I'll obtain the distribution of exposures, the concentrations. And on the basis of that, I can then say that, and this is now, I want you to look at the error bars on the left-hand side. So the model is predicting a much narrower band of uncertainty. So now we have two different estimates. They are actually kind of different from each other. One of them has a very large uncertainty extending well beyond the exposure limit. One is much narrower. So which one to pick? They are both, they both have their weaknesses. You can say the model is kind of simplistic, and I've assumed some uncertainty around it. I'm not sure if that uncertainty is actually accurate. On the other hand, I have these monitoring data, which are the gold standard, we assume, but we have only 3 of those, and it leads to a very large uncertainty. So how do we pick? Of course, we never pick, as you well know, many of you know. In this field, we typically use what we call an integrated exposure assessment. And we don't do it very formally, but we sort of do it in our head. And we start off, so in the top right-hand side, we can say, okay, my modeling, or maybe my professional judgment, is saying that this is a category 2 exposure, and I'm sort of 40% sure that it is in fact category 2. And it can come from professional judgment or some modeling exercise. And I took some monitoring data, and they're also predicting category 2. And my sort of integrated exposure assessment tells me that in fact it is category 2, because both my professional judgment and modeling and the monitoring, they all agree with each other. So I feel very confident about this. This has been formalized in what is known as a Bayesian framework. And in the Bayesian framework, the top figure is called as a prior. The middle one is called a likelihood function, and then the bottom one is called a posterior probability distribution. And so what we as industrial hygienists routinely do is in fact formally described by the Bayesian statistical approach. And so one of the things that I and many others in this field, many of my collaborators, we have sort of developed this Bayesian framework for assessing exposures. And there are a couple of advantages to this framework. One is that it is a very transparent framework where at the end of the day, you know what is the role that professional judgment played, what is the role that monitoring data played, and what are the sort of the relative weights that each one provided to the final integrated exposure assessment, or what is known as the posterior. So that's one thing. So it's a very transparent way in which all these different elements can be parsed. And the second thing is it leads to a very transparent decision making, meaning we know that the final result is a category 2. So we know, okay, that means, assuming that your company or your institution has agreed beforehand, okay, that means that we need to provide chemical specific hazard communication. So there is no question in anybody's mind about where and how that decision came about. So this is all great, but as you probably suspect, this works really well if our prior is accurate. And Bayesian analysis or industrial hygiene practice will be functional, and it will realize its full potential when we have accurate priors or accurate professional judgment. So consider 3 examples. So we'll start at the left-hand side here. So we have this professional judgment predicting a category 2 exposure. So that's 50% sure that it's a category 2. And you take 2 data points, and that's also predicting a category 2 exposure. And so both the prior and the likelihood sort of agree with each other, and they sort of lend strength to each other. And so the integrated or the posterior decision is also a category 2. So that's just great. But now we say, okay, what about the situation when our professional judgment is flawed, or at least doesn't match the monitoring data? I shouldn't say flawed right off the bat. So the monitoring data are the same as in the first case. So we are now looking at the middle column. So the monitoring data are predicting category 2, but the professional judgment is saying it's maybe category 4. So the final result, the posterior, is in fact category 4 in this case, because just the 2 data points by themselves don't provide enough weight to the final result. So the final result is driven by the prior. So we are suspicious of this result because, well, our professional judgment doesn't match what the data are telling us. So I guess the most common sense thing to do at this point is say, okay, well, I'm going to go and collect more data and see where we end up. Maybe I'm wrong in my professional judgment, or maybe 2 data points are too small to make this decision. So you go and collect now 8. Now your sample size is 8. And now, in fact, your final decision matches what the data are telling you, which sort of indicates that maybe you were wrong and not the monitoring data. So what this is telling us is if our professional judgment happens to be inaccurate, then either we end up with a wrong decision, like in the middle column here, or we have to spend a lot more resources and money collecting additional samples before we can overcome the effect of the erroneous prior. So both things are not great. So we wanted to look at how good are people's industrial hygienists' professional judgment accuracy when you have some amount of monitoring data. And so we did a bunch of studies where we did 2 types of studies. In this one, I'll just show you studies when we gather, I don't know, 30 to 40 industrial hygienists in a room, and we give them we show them videos of actual industrial tasks, and we also give them all the sort of ancillary information they need for completing their basic characterization of this particular work or this particular task. And we gathered, since this was a research project, we gathered a large number of monitoring data for each task. And so the way we would proceed is we would sort of ask the industrial hygienist, before showing them any of the monitoring data, what do you think where do you think the exposure distribution is? Where do you think the 95th percentile lies? Which category it is in? And so they would sort of say, okay, they would make their decision and say it's in this category or category 3 or 4 or whatever. And then we would show them the first data point, and then we'll ask, do you want to change your decision? And they may or may not change their decision. And then we would give them their second data point and our second monitoring data point, and ask them again, do you want to change your decision? And so we would go on until we have exhausted all the monitoring data. And so in this process, we obtained a fairly large number of judgments made by 124 industrial hygienists for about 30 exposure tasks. So we had what are called qualitative judgments, meaning judgments that the industrial hygienists made before they saw any of the monitoring data, and then about 5,900 quantitative judgments, meaning when they were able to see at least one data point. So our study design was sort of like an intervention study. So we would obtain their judgments, both quantitative and qualitative, before, and then we would do this data interpretation training intervention, because our team basically realized fairly early on that the industrial hygienist judgments may not be that accurate. And so in this intervention, we provided them some sort of basic recap of knowledge that they already had about log normal distributions and how to calculate the 95th percentile using relatively simple rules of thumb. And then we basically, after that intervention training, which took maybe about half an hour to 45 minutes, we then did post-training quantitative and qualitative judgments. And so here are some results. So the way to read this graph is as follows. So if the data that we had a fairly large data set for each task. The data predicted a particular category, and the industrial hygienist predicted the same category. That was considered to be a correct judgment. And so they would be counted in this middle column here. If the industrial hygienist predicted a category that was one below what the data predicted, then it would be counted in this below one, and so on and so forth. And on the y-axis, you have the percent of quantitative judgments. So there are a couple of things that immediately stand out. So let's look at the pre-training, pre-intervention data. We see the gray bars. We see that on average, the industrial hygienists make a correct judgment around, 45% of the time. So that's relatively low, I think. And as I and my colleagues like to say, you would not go to a doctor who has a 45% accuracy rate in diagnosing a situation. And the second thing is that there is a fairly large underestimation bias. So when we started our study, a number of industrial hygiene participants, they basically said, well, even if we are wrong in our judgments, we are probably going to be conservatively wrong, meaning we are going to be overestimating exposures. And that turns out to be not true at all. As a profession, we are underestimating exposures. So we are underestimating by one category most of the time. So the two things. So we are wrong, right only about 40 to 45% of the time, and we are also underestimating. The silver lining in this is that post-intervention, the rate of our accuracy rate increases significantly. It goes up to around 60%. And also the underestimation bias goes away. So the intervention, we just told the industrial hygienists to use these very simple rules of thumb. But what if they could calculate the 95th percentile each time using an Excel spreadsheet? And there are sort of many freely available software that do these calculations for us. In that case, our percent accuracy would go to 100%. So that's sort of the takeaway message, that anytime we have monitoring data, even if you have only 2 or 3 monitoring data, you should really go and use the statistical analysis rather than eyeballing it and trying to estimate it on your own. And lest we think that, okay, this was just sort of one academic study and who knows how much to believe in it, we have done this exercise repeatedly over many industrial hygiene conferences, and we see the same pattern repeated again and again. So all the way from Vancouver, it doesn't depend on country or state or anything. So we see a very similar pattern over time. Now let me look at the context in exposure assessment and epidemiology. So again, this was done for an industry where we had to reconstruct exposures over a 30-year time period. And there were 77 exposure groups. And again, just as in the previous study, we assembled these 8 company industrial hygienists. But now they had to provide their exposure judgments in terms of the arithmetic mean rather than the 95th percentile, since this was an epidemiological study. And so we were able to compare the professional judgments with what the monitoring data presented when both of these were available to us. And you can see that, so here the blue represents the professional judgment, so on the x-axis you see the arithmetic mean in 4 categories relative to a fraction of reference concentration RC, and you can see that the professional judgment is sometimes off from what the monitoring data are showing by at least 1 or 2 orders of magnitude. So again, there is a huge underestimation bias in the epidemiological context as well. Now, what happens when we have professional judgment accuracy when there are no monitoring data to use, which is, like I said at the beginning, almost 90% of our situations in industrial hygiene exposure assessment. So this was again a result of the study that I showed you before. And so here, of course, there's no intervention, so to speak. So we just have the data, the chart needs to be interpreted in the same way as before. So we see that the industrial hygienists are right about 30% of the time. Now, just to put that in context, there are 4 categories, and if you were just throwing darts on the board, you would be right about 25% of the time. So we are right barely above purely random chance, which is, of course, not great for professional judgment. So that's our random chance line at 25%. So how can we improve our knowledge or our performance when we don't have monitoring data? And so one approach is to, at least one approach that we came up with, was to use mathematical exposure models. However, these have not been commonly used in industrial hygiene. I mean, they are sort of increasingly being used, but still a very small fraction of the time they are being used. And there are a bunch of reasons for it. People have not really evaluated these models systematically. We don't really have much information on model input parameters, and there is very little by way of model selection and use guidance. And so what we did in this was a different study where we said, okay, let's use some very simple models that can be used by industrial hygienists in the field without too much expense and effort, although there is certainly some of that. So here the simplest model is what is known as a well-mixed room model, where you have this worker in an enclosure of any size, and we assume that the entire room here is well mixed and the concentration everywhere is the same at any point in time. And an example of this kind of scenario is shown in this photograph, where there is this worker doing drywall sanding of this wall. and is being exposed to airborne respirable dust and respirable silica. Um, a second, slightly more complex model is what is known as a near field, far field model. And here you have this room, this outer box, and within that there is a smaller enclosure, which is a smaller box known as the near field. The outer box is the far field, the inner box is the near field. And you can see a situation like this in this photograph on the right, where you have this worker in a pharmaceutical industry setting at a workbench doing a mixing operation, mixing several chemicals. And so her exposure at this workbench is represented by the near field concentration, and it would be different for somebody over further away in that room who would be exposed to the far field of this particular generation source. So how is model performance impacted in these very complex work environments? And so we had 10 field scenarios, and we very carefully were able to measure model inputs to the extent that we could. And we also accounted for the variability and uncertainty in these model inputs. And this is kind of a busy slide, but I want you to focus attention on the column on the left-hand side, and you can see a whole range of different types of work areas. So ranging from very sort of old style, dirty environments such as an iron foundry, drywall finishing that I showed you a photograph of, pharmaceutical industry settings such as weighing and transferring powders, salons, and then a degreasing operation where we are cleaning a mixer with acetone. And for each of these settings, we were able to uh, estimate what the generation rate and the ventilation rate and other parameters were, either as point estimates or known values or in terms of known distributions. And so these are some pictures. So that's the iron foundry. Um, this is a mold making operation. Sorry, that was a degreasing operation. This is the mold making operation. This is a salon manicure workplace, pharma industry, and then here's the drywall sanding again. And so we were, in many cases, we were able to estimate what the ventilation rate was, but we were not always able to estimate what the generation rate was. So in this case, we would not know, we didn't know what the generation rate was if this worker drywall sanded, a certain amount of wall in a per minute. And so how do we get that information? So we had to take a slight detour where what we did was we got this worker to come, and we set up a sanding operation in an exposure chamber, and we knew what the ventilation rate was through this chamber, and we were able to control everything else. And so this worker drywall sanded for a given amount of time, and we were able to back calculate what the generation rate was from this very well characterized chamber experiment. So anyway, so how do models work compared to random chance? So you can see the random chance. So when you have just random guessing going on, then of course the performance is very, very poor. But if you use these even very simple models, the well mixed room and the near field, far field model, the accuracy actually is astonishingly high, about 80 to 90%. So models do help improve our accuracy of judgments. So where are we now? So we basically, I've told you that industrial hygienists significantly underestimate exposures, but there are some tools available to improve accuracy. We can do better statistical analysis of small data sets, and there are mathematical models available to us. One thing I've not talked about today is there are various sort of heuristics and checklist-based approaches that also improve our judgment accuracy. So that's all great. But can we rethink all of this now? And So I want to talk a little bit about distributed low-cost monitoring networks. There are, if you remember, I said one of the reasons we got into this rabbit hole of looking at professional judgment is we cannot make adequate number of actual monitoring measurements due to their high cost. Well, so now we have relatively low-cost measurement methods. And the cost of monitoring for many agents has come down by 1 or 2 orders of magnitude. And so these graphs at the top, these are spatial maps obtained by one of my colleagues at Hopkins, Kirsten Kohler, at a workplace. And this workplace is, there are many of these low-cost monitors placed at different locations, and they make measurements at in real time or different time points. And so you have a continual spatial map of concentrations throughout the workplace. And then the traces you see, these are workers' movements that are being tracked by a GPS monitor placed on the worker. And so on the basis of the spatial distribution of concentrations and knowledge of where the worker is at every point in time, we can calculate an estimate of the worker's personal exposure. And in this particular study, the workers also wore a sort of a traditional personal monitor. And so we were able to, I shouldn't say we, but Kirsten and her colleagues were able to compare the exposures, personal exposures as measured by the personal monitors and compare them to the personal exposures estimated by the distributed low-cost network. And the figures on the bottom show that in fact these two measures track each other rather well. So there is a really good way in which for very low cost we can track people's exposures. There are other methods also that our team has been pursuing. So here's one where we can use reconstructive tomography, and this is sort of essentially a CAT scan. So on the CAT scans, which sort of originated in the medical field, are basically you pass X-ray beams at various angles through a cross section of a human body, and from the extinction of X-rays through these different paths, we can estimate the spatial density, the spatial distribution of tissue density. Analogously, we can say, okay, on the right-hand side, you see a hypothetical room, and those circles along the periphery are the light sources and detectors, and the light beams crisscross in this area. And from this, we can detect what the spatial distribution of a contaminant or the pollutant can be. And we have done some numerical simulations where on the extreme left you see a situation with a room with 3 different sources corresponding to the 3 peaks, which are of different magnitudes, with zero noise, perfect ideal measurements, what the reconstruction quality is. And if you have noise in your measurements, you see what the reconstruction quality is. You still can detect the 3 peaks. And what happens when you have about 75% of the rays, the light beams that are blocked by either the workers themselves or by machinery and so on. So with just 25% of the rays, you still get a very good reconstruction accuracy. And we've also done benchtop experiments showing this. So there's a lot of promise in this particular technology. But what does it all mean for exposure assessment? So if we are indeed able to assess workers' exposures using a distributed network or with this tomography technique, what it means is that we don't really have to monitor workers at the level of an exposure group. We can monitor each and every individual worker all the time. And so it can sort of lead to what I call personalized exposure monitoring. And so the decision chart on the bottom is not the decision chart for a particular exposure group that I've talked about in the past, in the previous slides, but this is the uh, risk profile for one individual worker. So it would radically change the way we do exposure management and risk management. So I would leave you with that thought. And so here are my sort of overall conclusions. So the first two I've spoken about earlier. Industrial hygienists significantly underestimate exposures, and this is uh, obviously a professional issue for industrial hygienists, but it's also an ethical issue because we are putting people at risk because we are, for a variety of reasons, not able to make the correct exposure decision. But there are tools available to improve accuracy, statistical tools, heuristics, mathematical models. But a way forward out of this low sample size conundrum is to use distributed low cost networks. And so that would change the paradigm in which with which we are assessing exposures. Of course, it will also lead to a different set of ethical issues, which I'm happy to discuss further. But that's where we are today. And lastly, I want to thank all the people and institutions who made this research possible, uh, the federal agencies that provided grant support for this, my doctoral students over the years, both at the University of Minnesota, where I was for many years, as well as Johns Hopkins University, and the many companies that helped with the professional judgment studies, the American Industrial Hygiene Association, and of course all the study participants and the workshop volunteers. So with that, I'll stop and thank you very much for your time. I'm happy to take questions.
Excellent. Thank you so much for a wonderful presentation. At this time, if you have any questions, please do feel free to enter them into the online Q&A box, and we will address as many as we can in the time that we have together. One of the first questions that came in, do these models take into account other environmental factors such as humidity and ambient conditions?
Yeah, so absolutely they can. So I just talked about the very simple models, the well mixed room model and the near field far field model, and and we have used them in the context of gases and vapors alone. Um, and so if we look at now aerosol particles, the effect of humidity would can be included, but it would make the model a little bit more complex. But that's okay. But that's the price we have to pay. It's always a sort of a struggle tension between simplicity of use and especially use in the field by field industrial hygienists and how fancy you want to get with your modeling. So there are certainly models that include all these kinds of effects, humidity and particle growth over time. And do you want to be sort of a steady state model or a dynamic model? All kinds of models exist, but it's like I said, you need to choose how much effort and resources you want to put into it.
This actually, thank you. And this ties into kind of a follow-up is noting just opening windows and doors could reduce exposure risk. And that they had asked a similar question if you're considering the variability in environmental conditions.
Um, Absolutely. So in in the iron foundry example that I very briefly went over, um, that study was that particular set of measurements were made in Minneapolis. There is a door that was very close to that particular worker who we were sampling, and in the middle of winter, that door is shut. In summer, it's open. So there is a lot of variability seasonally. And so our uncertainty parameter in the flow, airflow rate in that area would have to account for that variability. There are other sources of variability also, besides just doors and windows being open and closed, but that's like a huge variability that needs to be accounted for.
Thank you. Someone was also wondering if you were able to provide the link for the publication of the study being referenced.
I'm happy to do that. I will send that to you, Michelle, and maybe you can share it with everybody.
Yes, great, thank you.
Yeah.
And what I will do for everyone, on our website where you registered for this event, we will update the website page with the recording and also any references that are provided. And that will include the publication or link to that publication.
Actually, there are actually publications plural, so there's a whole bunch of them, and like any academic, I'm happy that anybody wants to get my publications, and I'm more than happy to share them.
Excellent. We will add some links for all of you to do your own continuing education after this presentation. Awesome. Another question, do you think that the lack of accuracy with professional judgment could be impacted by the background of industrial hygienists with respect to the processes they're evaluating?
Yeah, so that's a great question. So one of the things that we evaluated, and in fact, this was one of my students. I hate to call him a student anymore, but he was a student a long time ago. Perry Logan's dissertation, doctoral dissertation. But he did look at. We gathered information on the participants' background. So both in terms of the years of experience they had doing exposure assessment, years of experience they had doing exposure assessment for this particular chemical, um, the years since they'd last did any kind of exposure assessment, because people get promoted and they sort of go into sort of upper management and then they lose track of their basic skills. So that's possible. Um, their whether they have an undergrad, master's, or a PhD, whether they have a CIH or not, or other certifications, CIH, CSP, and so on. And so, and then the total number of years they've been in the profession. And so many of these things are significant. And so the main thing we found was the number of years of experience, as you might expect, that does make a difference. Um, Interestingly, although I hate to say this, audience, CIH was inversely correlated with accuracy. So people with CIHs were not as good as the rest, although it was a kind of a weak effect, but we did see that effect. Um, One other thing I want to mention is, I didn't show it today, but we did this. This was for when we looked at the effect of these heuristics and checklists. Um, and I didn't present any of those results today, but it looked like when you are, and I gave that one of my other students, Susan Arnold, who's now a faculty member at University of Minnesota. So we did that experiment with graduate students, master's students, and then sort of professional industrial hygienists, and we found that in fact graduate students were much better. And we don't know the reason for that, but we think that when you are a student, you are sort of much more sort of in the test taking mode. You're much more sort of, I don't know, conscientious. I hate to say other people are not conscientious, but there's like a grad school motivation that makes you want to do well in your exam. And so they were much better than the other professional industrial hygienists. So, yeah.
Thank you for sharing that with us. And this actually ties into another question. Someone was asking, what are the most important skills for industrial hygienists to conduct their professional judgments?
I would say, first of all, you need to really understand the workplace. And I know that's sort of fairly easy to say, but when I say that, I really mean that you need to start using mathematical models. And even if you don't use the models themselves, when you go out and you say, okay, I better understand what the ventilation rate is through this workplace, you are going to really understand your workplace much better than if you never thought about ventilation rates through your workplace. Similarly, if you say, okay, I need to understand quantitatively what the generation rate of this chemical is, um, you would really begin to understand what's going on in that workplace. So if I would say, so if you think quantitatively and try to understand your workplace quantitatively, that's, I think, a very good way to improve your professional judgment. I think quite often we are, uh, you know, um, we think we know what um, the exposure is, and quite often, as the studies have shown, we are quite wrong. I think having a modeling framework in your mind as you go about making judgments is better.
Thank you. And as a follow-up, someone was also asking if there's any standardized training that you could suggest.
So I would not say there's only one thing, but there are a number of PDCs that are offered through AIHCE, um, and uh, and I and my colleagues have offered it, but others also have, I'm not involved in all of them, but certainly there are plenty of professional development courses on professional judgment, modeling, statistical analysis of exposure data. So all of these things are available through AIHCE. There are the AIHA also produces uh, an exposure assessment strategy manual in which many of these topics that I touched on today are the full AIHA strategy is described in great detail. There are modeling monographs that are available. Um, AIHA also provides free software for doing the calculations of the 95th percentile and other percentiles. They produce free software spreadsheets for the models. So there is a ton of resources available, and just go to the AIHA website and type in these things. You will find them no problem. Or
Excellent.
you can send me an email, and I'm happy to send you the links.
Thank you. And that actually tied into another question, the models that you can recommend. And it sounds like the AIHA is a great source for some of these, whether it be a model or spreadsheet, etc. Thank you for
Yeah,
sharing.
so many of these, I mean, all of these models, certainly the two simple ones that I talked about, they are certainly available. There are more and more complex models that are available in the AIHA toolbox. There is even a chapter, although I don't think I would recommend it because it's too complicated, but there is even a chapter on computational fluid dynamics. So everything from the very simple to the really state-of-the-art, full-blown complex models are available.
Thank you. Someone had a very specific question from the Bayesian analysis example. Does it make sense to use the posterior results from n equals 2 as the prior for the n equals 6 instead of using the original prior with n equals 8?
That's a I mean, that's a great idea. Sure, yeah, absolutely, that's possible. Yes.
Thank you. We also have it's kind of a comment and a question. The AIHA Exposure Strategy Manual indicates that data for statistics should be collected randomly. Statisticians and biostatisticians indicate that the resulting statistics will be biased if not conducted randomly. In a factory assembly line, samples can be conducted randomly. But in a lot of other sampling, true random sampling is not as possible. So if an IH has conducted intentionally representative or diagnostic or worst case sampling, can these statistics be used without concern of significant bias?
That's a great question, and um, I mean, the person asking the question is absolutely right. That we need to have as close to random sampling as possible, um, and frequently we are not in this field for a variety of reasons. It may not often make logistical sense, not be feasible. So the very let's say you have a workplace with 3 shifts. The industrial hygienist is not going to go and take measurements at the midnight shift. He or she will do the daytime shift. So there's already a bias there. And so, and we are Um, so we acknowledge that. I mean, that's definitely there. And we say, okay, that's probably going to reduce, or that's probably going to reduce the variability that we can expect in our measurements. It can maybe reduce the um, overall levels. And so, I mean, there's no easy answer to that except that say, yep, you're absolutely right. We need to make a um, uh, better effort at getting representative samples. And this is where I think these newer technologies, the low cost sensors and so on, would be a great development because then you are going to be constantly monitoring everybody all the time. And this issue, it's a long time issue. It's by no means a new thing of biased samples and non-representative samples. It will just go away because we are going to be monitoring everybody all the time. But
Thank you.
that's a good question.
Thank you so much. And a special thank you to Dr. Ramachandran, as well as everyone who joined us for today's webinar. The Education and Research Center Industrial Hygiene webinar series will take place the second Tuesday of every month. And this series is in addition to our ERC Ergonomics webinar series, which takes place the third Wednesday of each month. Our next ergonomics webinar is going to be on Wednesday, December 16th. And we've partnered with the University of Texas Health Science Center at Houston and University of Iowa to offer a free webinar on fatigue in the workplace, effects on health and performance, and measurement considerations. We'll also be taking a brief pause in January, but we will be back to offering webinars again in February 2021. So be sure to check out our website for more information and to register for these upcoming events at coeh.berkeley.edu/about-CE. And you can also find the recordings to this webinar and the other webinars from our series this year on the COEH Northern California YouTube page. Thank you again so much for joining us today. Thank you for all of the information today, Dr. Ramachandran. I hope you all enjoy the rest of your day.
Great. Thank you very much for having. I had a great time, and I hope the listeners did too.
And thank you everyone for the wonderful questions and engagement today.
Bye-bye.
Bye-bye.